All right, so welcome to Compiler Design Part 2. In Part 2, we're going to build up a real compiler with a real language that goes to that compiles down to bytecode and can be executed on your system. Your program can be executed on your system. So I don't want to go through all the details of setting up the parser and the lexer. We went through that in the part 1 of this. So if you haven't gone through compiler design, go through that to learn about lexical analysis and parsers and all that. I've set up a skeleton project here that compiles. In fact, let's just double check that. Let's go into build. Actually, let's remove that. RM build. Let's make dir build cd build CMake dot make. And just make sure that this skeleton here builds. I kind of moved it over from my prep area. Yep, it builds. And we can actually run it if we're in the build directory here, ./source, and the name of our language is Socrates, and I'm going to go to my test.soc file, oops, -i, and it actually parsed it. So I'm going to go through how we're setting this up. I'm going to talk a little bit about the Boost libraries and show you the make files. All of this will be available on GitHub, so you can download the starter project from there and get rolling with it. Let's first take a look at the top level CMakelist Txt. So we need to set up to use Clang. And you can do this. You can like change your compiler within your operating system to be Clang, but I didn't want to do that because I have many projects, and not all of my projects use Clang. They use GCC, so I didn't want to change my system. So I set it up here in the CMakelist file at the top level. You'll want to set these up in any of these paths. If your system is different, if these are in different locations, you may have to adjust these paths, but this has all the tools that the system is going to need. And these are just setting up variables for CMake. Then we want to find the setup to find the Boost libraries. Now I'm going to link with static or with dynamic libs. So static libs is turned off and the static runtime is turned off. We're going to not load the debug libs. It makes things really, really huge, and we're not trying to debug Boost, so we really don't need those. And we have use the release libs, and we definitely want multi-threaded. Then we're going to use this find package Boost. Now I've got 1.73. If you've got a different version, you'll want to change this to your appropriate version. And then the components we're going to use, at least initially, is date, time, file system, and program options. And this is one of the first things I'm going to talk about, is how to set up program options. I've already got it written in here. I'm going to go through it. It's a little tedious, but I'll go through the code and show you how that's done. And that's so that we can have some nice program options like this -i, where I told it the source file, the input file. And we can have multiple input files. Then we're going to want to find package LLVM. It is required, and we want to have this config on here that tells it to run the LLVM configuration through this. And these are just a couple of messages to make sure that I found it. Then you want to set up some include directories. LLVM includers and LLVM definitions are the definitions that come with LLVM. Once that's all done, I added in here that I'm using standard C++ 17. We may use some features from that, so I'm using that. And if you got the latest version of Clang, it should support it. And then I'm just adding the subdirectory source. So here's the subdirectory, and let's look at the CMake file for that. We're going to need Flex and Bison in here. So I find the package Bison and Flex, and then this is the setup for Bison. We did this in the previous video, so if you haven't watched those, but you want to take a look at this, the names are a little bit different because we're using Flex and Bison a little bit differently. So it's going to produce socparser.tab.cc and soclexer.yy.cc are the output files from Flex and Bison. And then this is standard include directories. Be sure you get these, have these names right. And then down here, target link or target include directories. We want for Socrates, our output file. This is under our executable Socrates here. We're going to have the current source directories, the Flex include directories, and most importantly, the CMake binary directory, because these generate these files in the binary directory, and when it's compiling, it needs to be able to find them. So, and then we're setting up C++ standard for this build as well. Set the property for target for that, and then we set up our Socrates. We want the boost link libraries for Socrates, and later on we'll probably have to add some LLVM stuff in here. We'll do that later when we start working with LLVM. Initially, we're just going to build up our abstract syntax tree. So let's go to main and take a look at that. This is where I'm using some stuff from Boost, and what I'm mostly concerned about here is Boost program options.hpp. So program options is a little program within Boost that allows us to easily parse the standard kind of program options and set those up and have a little help screen print out very nicely for us. So the way I've done that is I've created a function here for parse options. And by the way, I'll very quickly show that to you, I guess. Under Boost, I'll show you where to find that. Let me bring up my browser here and get a tab. We'll pull that over here, and we'll go type into Google Boost program options, and program options here. Now you'll notice it says at the top here, this documentation is for an old version of Boost. That's what we found on Google. If you just click on this link here, it goes to the latest version of Boost. And I don't know that it says it on here, but it probably somewhere it does. Anyway, if you go here so program options, if you go to the tutorial getting started, you'll see that it explains here how to put stuff into program options, how to compile them, and how to extract the information. So that's how you find Boost. I'll put links to all of these things in the comment section on the video. Basically what we're doing is we're creating a program options description object. This is part of program options. We're calling it generic. That's the name of our, and we're calling it generic options. And then you just go generic.add options, and then within parentheses here, right after it, before the semicolon, you put in this kind of information. So version is the dash one, and V is the single dash one, the single letter. So if you type in, if we go source Socrates -V, it prints out the version, and minus version also prints out the version. And I'll show you how that's done in here. So we're just adding all of these options into these groups. The program description, then we're creating a new program description called command line options, and we're adding generic and hidden to it. I called it hidden, but it really isn't hidden. It's just specs. In fact, I'm going to change that. I may change that. So I just took this example out of the documentation and kind of fixed it up for myself. Then what happens is, once you've got that all loaded in, when you call this function, you will notice we're passing in the argc and the argv, and we're passing in a reference to our options object. I'll show you that. I put that in a file called defs.hpp. Options is just a struct. It's going to contain a debug level, some include paths, and input files. Let's go back to main. So let's go down to the main function and kind of walk through the program flow. So our main gets the options that we've plugged into it. Don't worry about this. That was an experiment. I was fixing some things with unique pointer, so that doesn't matter. I set up an exit code. That's just to determine how I'm going to exit the program. And then I create that option objects, just an option objects right here in main. We're avoiding global state, by the way, so the options are going to be passed into things that we need them to have it as a constant reference. That way nothing can change it and there's no global state. So what we do here is you'll notice that program options also uses something here called optional. Optional is part of the standard library. Optional, I've included it here. Standard optional means that this can either contain a string or nothing. Okay, and so if something went wrong here and it couldn't process it, it's going to return nothing. In which case that'll fail and we have no program options. So I'll show you how that goes. We can either return a string or we can return this, which means it's not null, it just means nothing. We're returning nothing. That's what optional is. Optional is either nothing or it's the thing you want. So, and strings can't be null unless they're, of course, a pointer, and we don't want to use pointers. So we are either returning a string or returning nothing. What this statement down here does, auto result equals process options, it gets that into that result. And you'll notice that it's a optional string. So if this is true, then we have a string and we can output it. If it's and we'll return our exit code. So what that means is this. It's not so much that something went wrong, it's this statement right here. So if we've asked for help, if we've got a help thing in our string here, instead of returning nothing, it's going to return the string that is the help message. So if we come down here and go minus minus help, you notice it prints out the help message. Well, the way that happened was it returned the help message that comes out of this program options blob. When we just take the program options, the command line options, and go, extract them using a pipe here, that will contain this help information, and then we just print it out. Or if it's a version, we return the version instead of returning nothing. Otherwise, we process all this and we set up our options. So the way that works is, if there's input files, now I haven't done, yes I did. Up here there's a default value on help, include path, input files, debug. Debug level has a default value of 0 and it automatically sticks it into our program options. And it puts the default value in as 0. So we start off with, if you don't specify a debug level, what this statement here does is when we, whether we have a debug level or not, it's going to put something into options debug level. So we're passing a pointer, we're passing the address of options debug level to this so that it can store that value into debug level in our reference up here. And you notice it's not constant. We want to update this. So that's what we're doing, is we're updating the options object that gets passed in. In the case of include path, we don't do it that way because we need to add the path to it. So if we've got an include path, then what we're doing is we're assigning this this vector as a vector. We're assigning what's in there as a vector to this include path, which is a vector of strings. And the same thing with the input file, it's a vector of strings, so we're assigning options.input files is the vector of strings that was produced by this. And you'll notice that up here where we defined it, this value is a vector of strings, and this value, where is it? Is a vector of strings. So that's how it's processing it. So we can put multiple include paths and so forth into it. So once it processes that, if it's a help, it just outputs if it's any kind of string result, it just outputs the string result and exits. If it's none, if it's nothing, then this gets skipped, and we call the compiler, and we're passing in our options object. And the compiler is a class that I created, and I'll show you that in a minute. So compiler is this one. We'll look at the header file. So this is our class compiler. You notice it's got the options that we pass in, and we just simply assign those. They're coming in here as options. So it's just data, so it makes a copy of it. That's not a problem. So that way, there's no chance of it ever being updated or changed or something for things and affect something, create some side effects. And we just have a simple run function. So let's look at the compiler CPP Pro. Here's run. And we haven't done everything in here that this needs to do. I've just got some test code here to call our compiler. But basically, we're creating this object called an SOC driver. I'll get to that. This is SOC is for Socrates, and my system seems to have paused there. Socrates driver. I'll talk about the drivers when we get into the parser process, but for now, the driver is simply the thing that's going to do the parsing. And what we do is we pass it in each one of these files. So I'm looping on the input files and passing them in. Later, we'll also pass into the parser other information, such as debug level and so forth, but we're not getting into that yet. That's basically how the process in this works. It calls this compiler, runs it. Running it calls the SOC driver. The SOC driver calls the SOC scanner, and so forth. And we'll get into how those work. These are code that I have written, and we'll use those in conjunction with our Lex file and our parser file. And so let me check the time here, see how we're doing on time. Oh, we're 17 minutes in. So that's just this is just kind of an overview of where we're going with this. I'll show you the little bit of language that I've created so far. It's fairly simple and straightforward. Right now, we're just an expression, and I use the term pillar. We probably should change that to program. I was just playing around, kind of being silly. Program. And there's expression. So we're typing the expression. I'll get into that. The typing system is a little bit different for this. We're not going to have a union like we did before, and that's because we're using this right here, variant. So we're defining this variant system here so that we can use more complex objects in our types. And for instance, in our type here is this, we've just got a string instead of a string pointer, which is nice. We can pass those strings around without having to worry about pointers. And we've got this, where is it? Float. Missing something here. Oh, this is of type. Oh, here it is. Expression is of type expression AST. Expression AST is just a using up here. Using expression AST is standard unique pointer expression AST, and I'll explain all that. This is just to clean it up, and so we don't have this kind of stuff hanging around in all those statements. We'll use using statements to do that, just to make them a little tighter and nicer, and it's a little bit better than type defs. We could do the same thing with a type def. We'll talk about unique pointers and how they work and everything. We're going to build this up out of unique pointers. All our abstract syntax trees can be based on unique pointers. So when the top level goes out of scope, it's just going to start, everything's going to go out of scope. It's going to start deleting pointers all the way down through the chain with no issues. And that happens automatically with unique pointer. And our lexer is a little bit different. I haven't added in all of the fancy stuff yet, like comments and stuff like that. We'll get to that. We'll add comments in here. But the lexer works a little bit differently too. We've got some different code in here because we're using this this scanner system with it to go with the variant system. So anyway, we're right about 20 minutes. So that's it for this video. It's just kind of an overview of where we're going with this and what we're going to start with. This is our starting code. This will be up on GitHub. I'll put the links to it and everything. I'm going to put each one of these stages in a separate branch. So this will be like branch episode 1, and then there will be episode 2 branch and so forth, and it'll be the starting code for each of those episodes, which will also be the ending code of the previous episode. So anyway, that's it for this video. Thanks for watching. I hope you liked it. If you liked it, hit that like button. If you really liked it, hit that subscribe button, and I'll see you in the next video. Thanks for watching.